Hi, thank you so much to your professor, your teacher, Ms. Matza, for asking me to come speak to you all today. My name is Kate, and I am a paleontology grad student. I've had a pretty varied and interdisciplinary background so far, and Ms. Matza believed that it would be interesting for me to come tell you some of that because most of it is at least tangentially related to earth science, and I am pursuing graduate study in the earth science field of paleontology right now. So my name is Kate, and I'm a paleontologist. Some major takeaways from this talk that I hope you'll get. The first one is that art and science make each other better. Art is a really valuable tool in scientific communication, and interdisciplinary professionals of any kind are valuable pretty much anywhere. Additionally, y'all are coming of age into a world with unprecedented challenges that nobody alive has ever seen before, so it's completely valid for you to be entirely original in how you approach anything in your life. Your novel connections between ideas are needed. Additionally, your unique experiences are going to contribute to your value as an employee somewhere. You don't need to be perfect at everything. You don't need to know exactly what you want to do with your life at age 16 or 17, believe it or not. Um, and of course, the environment is very important. And no matter what you decide to do with your life, there is an opportunity for you to do your part in pretty much every field. I have to add the disclaimer that I became a paleontologist entirely by accident. I originally wanted to be a marine biologist, but when I was in high school, unfortunately, some negative millies and the adults around me told me that I was not a strong enough student to pursue science, even though it was my dream. I was very strong in art from an early age, and I went to art school instead of pursuing my dream. Um, what I'd like to say about that is you should generally listen to adults. They're usually right about things, but if anyone ever tells you not to pursue your dream or that you can't do something, then and you shouldn't listen to that particular message because it's wrong. Um, so I transferred into a school that allowed me to be interdisciplinary between geology and art a little more than halfway through my art degree. What I would recommend you do, especially if you're not sure what you want out of life, is look into scholarships. Even if you don't feel like you're perfectly qualified for them, apply to a whole bunch because you win some, you lose some. It's how it is, like the lottery. It's not personal, and save yourself an insane amount of money. Just do it. You're good enough. Just apply. I do want to talk briefly about my art background. When I was in art school, I was a sculpture major in the SUNY Purchase Visual Arts Conservatory. I was involved with mermaid stuff and also animation and biological illustration. Even though I was technically a sculpture major, I was involved in the Susan Rockabilly documentary, Vision of Mermaids, in my third year at Purchase. I did want to pursue a double major with environmental science, but we were pretty heavily warned against doing that because it was a BFA program. And BFA programs are quite a commitment. So if you are interested in doing more than one major and one of those is a fine art major, definitely weigh the options with the different degree possibilities that you have in your department that you applied to. Dual interests are, I think, phenomenal. I had them, obviously, but I think it's especially responsible to pursue more than one major or a major and minor or whatever, particularly if you have a creative interest, just so you have plenty of career options. Here's some of my artwork from at Purchase and shortly after Purchase. You can see the heavy marine biology theme and also you know, the illustration theme as well, the biological illustration theme. I was drawing on some old-timey biological illustration for a lot of this. So when I did transfer into a program where I was able to pursue geology at SUNY New Paltz, um, I did not know, and I was very delightfully surprised by the fact that most geology programs in college require you to take paleontology, especially if there's a heavy teaching program at your school. Paleontology, for those of you who don't know, is the study of fossils, extinct organisms, prehistoric life. It encompasses dinosaurs, but it's so much more than dinosaurs. Most fossils are oceanic and are invertebrates. So there's a wide range of things within paleontology. Luckily for me, as somebody who arrived from an art school with no scientific training outside of high school and no math classes, I felt very behind everyone else. But luckily for me, the paleontology professor at New Paltz is very influenced by a legendary paleontologist named Dolf Seilacher, who swore by drawing every fossil you encounter so you understand its form on a very intimate level. And because I could draw really well, my professor took notice of me very quickly. It turns out that professors really want to support you in your interdisciplinary pursuits. So don't be shy about that if you have them, if you're interested in more than one thing. If those things connect in a way that you want to pursue, do it. People will support you. And this particular professor handed me opportunity after opportunity. I was a research assistant, I was a teaching assistant. He got me involved with a museum upstate, and I was in their exhibits. I did fundraising with them. It was pretty cool. So here are a couple of drawings I did for my first few classes with that particular professor. The top right is a modern coral called Acropora. The top left is a modern coral called Acropora. The top right is an ancient coral about 420, 430 million years old called Hexagonaria. The bottom left is a modern conch. The middle image is a modern horseshoe crab, and the bottom right are some clams. I believe that they were modern clams, but a long time ago. I don't know for sure. An interesting thing about marine invertebrates that you might find on a beach is that most of them would fall into the living fossil category. So that was a pretty interesting thing for me. Gonna throw some new terms at you, probably new terms anyway. Paleo art is the visual and artistic depiction of prehistoric organisms, environments, and events. Paleo environment is an ecosystem from prehistoric times. It's usually known to us from a fossil assemblage, which is a group of fossils that are all found together. We can work to piece together a paleo environment from the fossils by interpreting how they were likely to have interacted with one another, and also non-living, non-organic things in the rock record, like water energy in the environment, if it's like crushing waves or if it's still water, climate, and a bunch of other things. And then finally, an ammonite or an ammonoid is an extinct type of cephalopod most closely related to an octopus, except it has a shell. It looks like it would be more related to a nautilus because of the shell, but it is closer to octopods and squids. On the picture on the right, where I'm drinking a Diet Coke, I am holding a very primitive fossil that I had just found on the ground of a very, very primitive ammonoid called Agoniatides expansus. It's within a concretion, which means that immediately after it was deposited after death, inorganic silicate material sediment packed around it, as inorganic silicates are wont to do in the environment, and it creates a shell around organic acidic material, and it preserves things. It's a very common way to find fossils, especially marine invertebrate fossils. So here are some images from trips from my time in the geology department at SUNY New Paltz. So you can see my friends at the top left. The top middle image, we are going to circle back to, it's important. This is a very, very ancient nautiloid, which is basically a chambered nautilus with a straight shell. It has not yet evolved a coiled shell. And if you notice these septa or sutures between each chamber, are these smooth little crescent shapes. That's going to be important later. Keep it in mind. Nautilus has a smooth septa. Then these things on the right are called brachiopods. They look superficially like a clam, except they're more closely related to corals and bryozoans. The reddish fossil on the bottom in the middle is a bryozoan, which is a coral relative, and the tubey thing on the far left is a pyrrhotized coral fossil from the Silurian period called Syringopora. So luckily for me, I sensed an opportunity fairly early into my paleontological career. Um, every year, my paleo professor would spend approximately 30 seconds on the subject of a subset of the ammonites called the heteromorphs, which have the most bizarre shells ever. And on a field trip in a museum, I saw one and I was very inspired by it. I realized that there wasn't a lot of paleo art depicting them, heteromorphs, and of the paleo art that did depict heteromorphs, not very much of it was depicting them as unique species, meaning that in modern cephalopods, like an octopus or a squid, or a cuttlefish, you have a plate of shell on the inside of the organism. They've internalized their shell. So an octopus, you call it a stylus, a squid, you call it a gladius, and on a cuttlefish, it's a cuttle bone. So these things don't really look that different than each other most of the time. It's just a flat piece of calcium carbonate most often. And yet these cephalopods have incredible biodiversity. They're incredibly disparate, meaning that their appearance is very, very different from one another. And yet there's very limited difference in their beak structures and in their internalized shell structure. So if they have all these differences, and we don't see in their soft tissue, and we don't see that many differences in their hard tissue, but we have these shells from other cephalopods that are very different from one another, and these beaks that are very different from one another. Why are we reconstructing them all to be basically just the same random squid in a shell? So this was something I challenged about 5 years ago for the first time, and I just did one heteromorph after another, and it just became a thing, and I became very hooked on doing it. I want to reiterate that I'm not the best at math, and yet I am a paleontologist. Not as terrible as the text may indicate, and I'm not saying that you should not give it your best effort. You absolutely should. Um, but if you dream of being a scientist and you're daunted by the math, I really don't think that you should be, even if somebody told you that you're no good at math. Um, what I learned from joining a science department is that everybody struggles with math and everybody feels like they're not good enough. And that's no reason not to follow your dream. Someday you'll prove yourself wrong. Here are some images from the very first heteromorphs, and these are mostly heteromorphs. The green little one in the middle on the right is a Goniatides expansus, but the rest of them are heteromorphs. And I drew these pretty quickly within a few months. And I have some references on the table, just a regular ammonite, Acanthoceras, and a chambered nautilus shell. Heteromorphs are pretty rare. I didn't have any at the time when I started this project, so I was relying on digital models and photos and all sorts of things. So we're going to talk about a few more terms. Ontogeny is an organism's life cycle and the physical changes that it undergoes. And this is especially important in heteromorphs and other ammonites because in heteromorphs specifically, the shell will start as a little baby cone and then it'll become an open coil, and then it becomes an open coil with a straight part, and all the time the orientation of the shell is changing throughout ontogeny because the phragmacone, this is called, the parts of the shell that are chambers are filled with gas most of the time, but the living chamber is filled with the meat of the animal. So that has weight and this has buoyancy. And so throughout ontogeny, a heteromorph's position is going to change, which is important to keep in mind. And then a fractal is a mathematical phenomenon where you have an infinitely repeating pattern of subdivision where the subdivisions are identical to the whole. So on the right, we have a GIF or a GIF of the Koch snowflake, which is one of the prime examples in geometry of a fractal. I'll just let you guys watch that for a minute. Okay, so fractals are important in, oops, I went too far. Okay, fractals are important in studying ammonites because there are two types of things we call fractals. I'm going to go back to this for a minute. So the thing in the GIF is a true fractal, which does not exist in the three-dimensional universe, because eventually you subdivide and you subdivide and you subdivide, and eventually you get down to molecular and atomic sizes and you can't go any further. So we have things in the natural world which are called natural fractals, which in contrast to true fractals do have an endpoint and they stop somewhere. And plenty of things in the natural world that we consider natural fractals can be mathematically approximated using the same type of math used for a true fractal. So this isn't very fractally quite yet, bear with me. This ammonite is called Didymoceras cheyennis. On the left is one of the first drawings I ever did of a Didymoceras, and we have an ontogeny going from early ontogeny to late ontogeny with this just generic ammonite symbol. And so the baby one, you can see I've blown it up here. It's got very delicate little arms that you can't really see, but then as I have it maturing, the Didymoceras, I have these muscular octopus-like arms happening. And part of the main reason for that decision, I want you guys to look at these two squiggles, which take us back to our natural fractals. So each one of these squiggles, if you remember, I mentioned the nautilus has a smooth septa. The ammonite has a crazy septa, which is made of natural fractals. And so this is a section of the septa of the ammonite called a lateral lobe, hence the letter L. The reason I only have part of the septa is because juveniles or baby Didymoceras are so rare. Any Didymoceras is so rare, but a baby Didymoceras, little known one where you can see the septa, was impossibly rare. I searched for one in every collection I have contact with for months. All we got was one from the Didymoceras cheyennis. I've included my tracing of it here, and you can see those. You can see that there are some major differences. You'd expect it to get more complex over time, but the elongation by adding folds to the base specifically of this lobe, so it gets stretched out, is something that may, in my opinion, probably influence the functional morphology or how the animal was able to behave based on its own adaptations throughout its life. Heteromorph doesn't just mean weird shape, it means many shapes. So these animals went through multiple life stages, possibly age segregated niches. So the little ones were doing something different than the bigger ones. And we're going to get into what these differences in the septa possibly mean in a little bit. For now, just accept that they probably mean that the big Didymosauros was lower in the water column and was possibly more muscular looking proportionally to its body than the baby one, because it was probably eating something completely different. This is another member of Didymosauros. This is Didymosauros nebraskans, and I didn't have septa for it, so I just extrapolated what I thought it was doing based on the septa, the juvenile septa that I had. And then this is Didymosauros stevensoni, and same story, didn't have enough septa. Okay, so one of the things I should also touch on here is I've organized all of these Didymosauros in a descending pattern where the adults are closer to the bottom and the juveniles are closer to the top of the page. That's for a reason. I don't know that it was perfectly linear necessarily as I have it, but how do we know where ammonites live relative to the seafloor or the surface of the ocean? So I have another heteromorph here. This is called Scaphites. It's from the western interior of the US. It would have lived alongside some of the Didymosauros. This thing has on the back of it, and this is also a heteromorph, it's just a simpler one. On the back of it, we have this little triangle here, these little concentric triangles. This is actually a piece of an enormous ancient clam that lived all over the world throughout the Cretaceous period. It's called an Inoceramid. So Inoceramus was actually not only a great index fossil, so it can help us organize time because it's all over the world for just a brief little slice of time. But many of the inoceramids that we have their original calcite, their original shell material. All shells are made out of calcite or aragonite, two different mineral structures of the same basic chemical composition, calcium carbonate, which is calcium, carbon, and oxygen. Two of these elements within calcium carbonate are very important in determining where any sea life with a shell will be positioned relative to the surface of the ocean. So basically, Inoceramus, it's a clam, right? So it lives at the bottom of the ocean, and we even find it in deep water where we know that there was no oxygen because Inoceramus is one of the only things that we see there. So we don't see a ton of cephalopods, we don't see fish. All we see are things that don't need a ton of oxygen to survive. But they live kind of everywhere, so you can find them where there is oxygen too. So basically, this one is just a cast. It's a naturally occurring cast, but there's no original calcite here. However, if I had an Inoceramus with calcite, what I could do to test my Didymosauros and my other ammonites is I would find the stable isotope ratios in the calcium carbonate that is preserved. So for a benthic or a seafloor heteromorph, the stable isotope ratio is going to be similar to a benthic inoceramid. And for a superficial heteromorph, the stable isotope ratio is going to be flipped from an inoceramid. So generally in surface waters or also water near the equator, water near the shore, generally water that's warmer, because you have evaporation taking place, you're going to have heavier oxygen isotopes because isotopes exist everywhere. And so you have um, atoms of the same element that don't necessarily have the same atomic weight. So, so you can have heavier oxygen and lighter oxygen, and they're both in water. And so basically, when you're at the surface and there's evaporation, the path of least resistance for the evaporation process is to grab all the lighter weight water molecules first. So these are the ones with the lighter oxygen isotope. And that leaves behind the heavier oxygen isotope, which means that they are going to have a heavy oxygen isotope mostly. Meanwhile, in the benthic region on the seafloor, we have all sorts of detritus and organic matter sinking to the bottom. And this matter is rich in delta carbon 13. So as opposed to delta carbon 12. This stuff all has delta carbon 13. And so that carbon is being incorporated into the shells of the animals on the seafloor, but not the animals at the surface. So the animals at the surface have depleted carbon 13, and the animals at the bottom have have enriched carbon 13. And then because there is no evaporation, or there's much less evaporation taking place at the seafloor, it's not that we have it's not that we have less heavy oxygen, we have more um, of a mix. So we have a little bit of a varied thing happening with the oxygen, but we have very high C13. Whereas in the surface water, we have very high O18 and very low C13. I hope that made sense. So in my professional life, this is a very cool thing that happened right up until around the time that I went to grad school. I was the paleontology specialist for the Astro Gallery of Gems on Fifth Avenue. And so basically, Astro is a historic gallery in New York City. It's the oldest and the largest commercial mineral gallery in the world. And you can see here, I'm in front of some Russian St. Petersburg ammonites called Spinosaurus, and you can see some megalodon teeth. The spiny thing that looks like it's growing out of my head is a giant Spinosaurus tooth. In the middle, there's me with a primitive heteromorph, and on the right is me with an Eocene age freshwater stingray from the Green River Formation, which is in the middle of the US, and that stingray is called Heliobletus. So this is me at the gallery with a huge heteromorph, about a 3-foot long heteromorph called Ankylosaurus dendenhecki, and the right is my reconstruction of Ankylosaurus dendenhecki. This ammonite sat on the gallery floor for about 5 years before I put a drawing in front of it, and it sold within a few weeks of me doing that. Ankylosaurus is a very primitive heteromorph. It doesn't do anything that crazy. This thing though is massive, and it retailed at $10,000. That was pretty cool. These are some trilobites that I arranged, and I did the lighting for it. Not a great picture of them though, but it's the only one I could find, so I'm sorry about that. So all of these trilobites are from St. Petersburg, Russia, and it's a little interesting to talk about them because this perfect preservation of trilobites only occurs in geological events called turbidite sequences, which are underwater landslides. Principle of fossil preservation is that the faster after death something is preserved, is buried rather, the greater the likelihood that it will be preserved. To have perfect preservation, you generally need for something to be buried alive, which is unfortunate for them. But it's part of why they're all in these like weird positions. Some of them are like bending upwards, like trying to get out of the. It's very sad. Um, but it's also gives us great fossils. On the right in the front, we have some trilobites with very, very small eyes, which evolved from trilobites with enormous complex lens eyes. And this is important for me to point out because these trilobites would have lived at the far reaches of the continental slope and their victimhood in a landslide. And it's also hence the spines on the very decorated looking one. This is Dicranurus monstrosus. It's an odontofluorid trilobite, which is a type of trilobite that had really tiny eyes and really long spines. And the reason that it has these spines is probably related to some form of a snowshoe adaptation, which means that basically at the distal end of the slope, the farther you get out into the ocean, the more fine-grained and the more mafic the sediment is going to be. So you get it's the most weathered material because mafic material is the most vulnerable to erosion. So you get out there and it's all very, very fine grained, which means that the seafloor is mud. And anything that is not able to offset its own weight could just sink into the mud. And so unless it's like a fossorial or a burrowing animal, it probably doesn't want to do that. And so Dicranurus and some other animals have developed these very long spines to prevent themselves from sinking into the mud. Um, in the middle is a trilobite called Parasaurus exel. It may have had a similar thing, or it may have been the spines on this particular one may have been more of an adaptation to sink out of the way of a predator without appearing like it was darting away for its life. It may have been just like a falling piece of organic matter. There have been models, a lot of these trilobites, not necessarily Parasaurus, but that general shape, to have done this all the way down to the seafloor, and it looks like a falling leaf or a falling piece of some form of organic material. There weren't leaves out in the ocean, but it could be like a piece of a dead fish or a piece of seaweed or something. I don't know. And then the other trilobite in this image I really wanted to touch on with you guys is the one at the back left. It really has no ornamentation at all except for the fact that it has very long stalks for its eyes. And we believe that this trilobite may have come around at the time when fish became a predatory force. So this thing could very easily sink under the sand and just keep its little eyes out like a periscope and just look out. And when the coast was clear, it would continue on its way. So yeah, trilobites are pretty cool. They're very diverse. They're amazing eye adaptations, amazing ornamentation. If you're interested in paleo, I really recommend looking at trilobites. So then another thing that happened a few years ago was I was a special mention finalist in the International Award on Scientific Illustration, which is an annual competition organized by the Spanish National Museum and the Catalan Association of Scientific Communication. The image that I almost won the competition with is at the bottom right here, and I'm planning to re-enter this year with another image I'm working on for another paper, which will hopefully appear in Springer Nature, which is like the big science publication. So that's the goal. Shortly thereafter, I was the featured paleo artist for Fossil News magazine, which was pretty cool. It's a great magazine. They get a lot of like different perspectives on a wide range of things in paleontology, whether into dinosaurs, pterosaurs, fossil plants. They have had a lot of interesting people. So in terms of my current and future plans, I have that paper that I showed you guys some figures from my Didymosauros paper, the Paleoart theory of ammonites, using Didymosauros as the main example because I've done so much work with them. I'm currently in the last semester of my master's thesis, and I just applied to a whole slew of PhD programs, probably going to apply to a whole slew more. I'm working to put together an invertebrate paleoart society, and also I do a little bit of work with living invertebrates, particularly arachnids. So back to that fractal GIF for my master's thesis. Again, fractals, there's two kinds. There's natural fractals and true fractals. Ammonite sutures are a natural fractal. And I've been developing a way to measure the change in the fractal value over the ammonite's ontogeny, or over its life cycle. And I'm looking for distinct patterns between different groups of ammonites, specifically between Lytoceratids and what I like to call regular ammonites. And there's some other regular ammonites by me. There's probably no such thing as a regular ammonite, but Lytoceratids have much higher fractal values than any of these other things. Okay, so then I'm determining the patterns and the ranges of these values to extrapolate differences in the functional morphology of different groups of ammonites, which we are going to talk about in a minute. Here's an example of different patterns and different ranges. The x-axis I want to talk about for a minute because it says world number. So that means that you make a full cycle around the shell in terms of its growth. So a full cycle is a world. So you have multiple sutures within each world. That's why it's so spaced apart like that. Each one of these is a different Lytoceratid, and most of the more derived forms have this scalloping pattern in terms of their increase of complexity so far. This particular chart doesn't have any non-Lytoceratids on it, but their values would be lower, and the gap between Lytoceratids and non-Lytoceratids should widen over ontogeny. Okay, so this is the comparison between a Lytoceratid and a regular ammonite, and why this is important. So if you remember, we talked at the beginning of the presentation about the nautilus and how it has a very, very simple septa. It's just a smooth shape. And if you notice, if you haven't seen a nautilus shell before, it's fairly thick. It's probably like 1/10 of an inch thick, the shell and the septal walls. If we go back to the ammonite. So ammonites did not have the same shell thickness as a nautilus. And this is important when understanding why ammonites had such crazy septa. The reason that ammonites probably had thinner shells is due to life cycle being more rapid than a nautilus. A nautilus lives for about 20 years, including modern nautilus. They live for about 20 years, and it's thought that most ammonites, with a few exceptions that were pretty extreme, most ammonites live for about 4 or 5 years. So when you have to spend all this time and energy creating a calcite shell, which is actually a very energetically costly process in nature, something that lives 4 or 5 years is not going to be able to produce the same thickness as something that lives for 20 years, even if they're doing the same thing, which they probably were. When you have something that goes up and down in the water column, it needs protection against being crushed by the change in pressure. So the Nautilus does this. The Nautilus, which has all the time in the world, does this by just having a very thick shell that it can take all the time and energy that it needs to deposit a really thick, simple shell. Great. It's worked for millions of years. It's still working today. Wonderful. Something with a sped up lifespan does not have the ability to deposit calcite or calcium carbonate at that same rate. So if it's also going up and down in the water column, it has to do something a little bit more creative than just deposit a ton of material. And so it has to get really efficient with that material. And so that results in creating these folds. So if you fold a piece of okay, so if you take a piece of cardboard, let me grab a piece of cardboard, the cardboard box. Okay. You take a piece of cardboard and you sand it up and it doesn't have any folds in it. If you put pressure on it, it's going to collapse, right? Yeah, okay. Sorry, nice to see the background. You can try this though. Stand up a piece of cardboard in your classroom without folding it and put pressure on the top edge of it and see what happens. It's going to collapse, right? Now try putting a couple folds in it and do the same thing. Put pressure on it, and maybe you put too much pressure, it shot away. But if you put the right amount of pressure, it didn't move. And this is a physics principle called tensile strength. It's the ability to withstand pressure because you've added folds. And so ammonites were probably reducing their need for thickness by adding these folds. However, it's not clear that every single ammonite species or group was doing that. So at the top of this painting, this is a painting I did for my thesis, we have this little shoal of Dactyloceratid, which are a regular ammonite, and their suture, you can see it on the right here. It's very, very simple. And if I were to fractally analyze it, because it doesn't branch out as much as the Lytoceratid suture, it would be a much lower fractal value. And these guys, you wouldn't necessarily see a whole stream of bubbles in the wild if you watched a cephalopod jet propel, but I felt like it was more attractive than using arrows, so I did bubbles. So these guys move horizontally, and the Lytoceratid is moving vertically. You'll also notice that the pupils of the Dactyloceratid, the regular guys up here, because they're up near the surface, their pupil is really, really small, and the pupil I've given to the Lytoceratid is actually very, very wide. This is because modern cephalopods, which we have to base a lot of our reconstructions on ammonites from, modern cephalopods will actually change their shape of their eye, specifically giant reef cuttlefish. Depending on the light that they're in, the pupil will open or shut. Our pupil does this too to an extent, but the entire shape of the pupil can actually change depending on the light that the cephalopod is in. So that's just another little detail. So community projects that I'm involved with within paleo, in addition to the things I've shown you, I'm pretty involved with a few things related to the fields to try and improve things for posterity. One of the main ones is diversity. Paleontology and the geosciences in general are the least diverse of all the scientific fields, and science is already pretty lacking in diversity. Additionally, paleontology is kind of filled with a bunch of creepy old men who aren't always the most kind or courteous colleagues that we have. And so my generation of paleontologists has been working to change this. Some examples of things we do are we put pronouns in our professional profiles. We hold bullies and bigots accountable for their actions. And we try to educate each other as best we can on different biases that exist between different groups of people so that we can overcome them together. Some things that have happened to me as a woman, especially a young woman in this field, are that I've had men assume that I was lost at paleontology events and assume that I didn't belong there. I've been standing next to my work and had men come up to me and explain it to me, and when I told them that it was my work, they've kind of argued with me and said it couldn't possibly be my work. I've also had like creepy things happen. The reason I'm telling you this is so that you know that all of you, regardless of your gender, your race, your socioeconomic status, your ability, whatever, every single one of you has the ability, has the right to say something when anyone makes you uncomfortable ever. And if you can, I recommend trying to document things. Um, it might really help you somewhere in a tight spot if you get into a field where you feel marginalized. It might be a good way to protect yourself. Obviously, nothing that ever happens is your fault like this. And you do always have the right to say, I am uncomfortable with this. You really do, no matter what. Um, However, I still have a relatively high amount of privilege within the field because the field is pretty much all white people, even still. Um, so I try to support my friends who are of identities that I am not. Um, this is my friend Cam Muskelly. Cam is the young, oops, sorry, I'm trying to move my window so you can see this picture of Cam. Cam is the youngest ever first person of color and first openly autistic recipient of the Catherine Palmer Award, which is the most prestigious award in the world for non-professional paleontologists. It's awarded to one person every year by Cornell University's Paleontological Research Institution and Museum of the Earth. I am proud to say that I nominated Cam for the award, and he really deserves it. He works so hard to increase diversity and accessibility for everyone in paleo. Cam has created a bunch of museum outreach programs at some of the major museums in the greater Atlanta area, including the Fernbake Museum. He has endured more than his fair share of bigotry in and outside of paleo. And he's worked very, very hard on harnessing the power of social media for science communication to make science education more accessible to people who, due to socioeconomic status or ability or both, can't receive a traditional college education in the geosciences right now. So he's just an all-around great guy. He's one of my favorite people in the field. And yeah, um, this is another project of mine. It's an advocacy project for arachnids and particularly the emperor scorpion. It was born of my beloved pet emperor scorpion, Christine, having babies. You can see her in that one picture with all her babies, and the picture immediately to the right of it, it's also her. The picture on the far right is her son, Fred. And I've included a couple other pictures. This is something I run with my friend Vanessa out of San Antonio. Vanessa also keeps and breeds emperor scorpions, and so we advocate for arachnids and particularly emperor scorpions, and we just try to keep the species alive for posterity in what way we can. They're pretty easy to breed, so it's not that hard, but emperor scorpions did get hunted nearly to extinction in the wild in the 80s and 90s because they're really friendly and they're really big and everybody wanted one for a pet, so they were all wild caught, and a whole bunch of them just were taken out of the environment, and not very many were left behind. And then ultimately they started to have a resurgence once the species was put on the endangered species list sites, but they haven't rebounded to their original numbers or even close yet because of habitat destruction in their native region. So this is a project that means a lot to me and my friend. Emperor scorpions have anti-malarial compounds in their venom. We don't exactly know how important they are to the environment, to us as human beings. But from an ecological standpoint, um, I just love them, and because they are so friendly, they're a wonderful ambassador for helping people to get over arachnophobia and fears of creepy crawlies, which is something I'm also passionate about. Um, you know, invertebrates are such an important part of our ecosystem, and they are animals and they do have emotions. I've, had feelings, and I don't know, I'm getting all soapboxy here, but I love them. I want to protect them. This is my initiative to do so. Feel free to check it out. Um, in addition to emperor scorpions, I'm a fan of all sorts of arachnids, and if I didn't say before, arachnids include spiders, scorpions, ticks, unfortunately, because every family has a doozy, and also the amblypygid, which you may have seen in the fourth Harry Potter movie. The thing from the spidery looking thing from Professor Moody's class is the amblypygid. Horseshoe crabs are now recognized as arachnids, which all of us in the evolutionary biology world wanted to happen for a very long time, because the only real difference between horseshoe crabs and other arachnids is that they're marine and they have book gills instead of book lungs, which isn't really a difference because it's a very simple structure. It's pretty similar to a book lung, and also scorpions and other very ancient arachnids came out of the ocean and are virtually unchanged, with the exception of their foot structure and their respiratory structure, which, as I said, is very similar whether it's on land or in the water. Um, so I love arachnids. The three arachnids on the left, the scorpion and the two spiders, are mine. The scorpion is an African burrowing scorpion, Opisthothallus glabifrons. Her name is Beatrix. She's really old. I've had her for years. And when she was younger, she used to dig these incredibly heteromorphic burrows where it's just like winding around. It was amazing. In the wild, they can dig meters and meters underground. It's really incredible. The black spider is my Brazilian black tarantula, Joanna, and the very fuzzy spider on the bottom is my Nicaraguan curly hair. Her name is Tinsel, and she's almost as avid a burrower as Bee used to be. So, and then the horseshoe crab was found dead on the beach. No horseshoe crabs were harmed for this picture. It's a deceased mature female who probably lived out many breeding cycles and then lived out her life cycle. And then this is a project that I recently took up with some good friends of mine in the field. Um, Paleo art generally excludes invertebrates. It tends to be very vertebrate and especially dinosaur centric. So because of the ecological significance of invertebrates and because there are so many incredible things like heteromorphs, like arachnids, that people don't get to see, like the Devonian reefs, like there's so many things that people don't get to enjoy because they're only exposed to dinosaurs. And because, as I mentioned, the ecological significance of understanding invertebrates would really probably help people to understand the problems with the environment now. um, we are creating a society for people in paleoart and paleontology who choose to showcase invertebrates as central figures, as complex organisms, and not just as background or filler or food for vertebrates. And so this is a pretty exciting thing. Um, yeah, I'm just very excited about it. It's going to be awesome. This is a work in progress. This is the first heteromorph I ever saw in person. It's called Nipponites. It's from the Hokkaido island in Japan, the big northern island. And it's from the Turonian, which is in the Cretaceous period. Nipponites is kind of a mystery to a lot of people because its shell is so insane looking. It doesn't make any sense. We don't know why it evolved this shell shape. I did include some brown seaweeds in this reconstruction, which was taking a really big risk and is probably going to be met with a ton of controversy in my field because seaweed generally does not fossilize even in paleo environments where you would expect to find it. We do know that there was brown seaweed, brown algae alive on Earth at this time and before this, so I took the liberty of including some and I'm still roughing them out, as you can see from this picture. Even though it was a controversial decision to include them here, the reason I included them here, And the reason that they are not touching any of the Nipponites in the reconstruction is because this knotted roundabout shape of Nipponites is went through a lot of bad interpretations over decades and decades. People used to ascribe to Nipponites a mode of life called pseudoplanktonism, which means that basically it gets hooked onto something from one of these crazy meanders, just gets wrapped around a kelp or a driftwood or something, and then it just is stuck on there for life and doesn't swim, and it just filter feeds. And we have no evidence that Nipponites held on to anything for life, so we don't reconstruct it that way. And so even though we don't have actual fossils of the seaweed, we know that they were alive at this time. And so I've decided to include seaweeds that are not in a pseudoplanktonic relationship with Nipponites to show that Nipponites was not doing that. So it's controversial, but you can see that it's really not. And then this is very exciting to me. This is a new heteromorph that was reported for the first time last month. It was discovered by acquaintances of mine in Hokkaido, Japan. And like the thing with the Didymoceras, Nipponites should generally be up nearer to the surface. And this thing is called Sormites. It should be resting or hovering near the bottom of the seafloor. And these things we know probably had pretty serious beaks, and they probably just sat upright waiting for something to drift by. So the interesting thing about this group of fossils is that these three were all found together, and they're all in the same genus. Currently, they're all classified as the same species, which can happen. Ammonites, and especially heteromorphs, are prone to a phenomenon called intraspecific variation, which means different shapes, different variations within the same species. So we probably have an immature female on the right, an immature male in the middle, and a mature male on the left, if that makes sense, because the female will grow to be larger than the two males. So something that's very interesting to me as somebody who's both a paleontologist and a paleoartist is I'm abreast of all these new discoveries, and I get to be right there, and I can make a reconstruction as these things are happening, as I've been doing with Sormites. And there's another very close Didymoceras relative that just came out too, and I'm a little backed up on these art projects, so it's probably not going to happen right away. But yeah, so that's my whole presentation. Thank you all for listening. Again, thank you to Ms. Matza for inviting me here. Definitely email me any questions you have, or have Ms. Matza do that. Try to answer anything I can. Good luck to any of you. Hope you all got something out of this, and have a great remainder of your high school career. Good luck to all of you.